Okay, so I'm finally going to put out the opal video because I'm not completely happy I fully get opals, but I think that's where we are at the moment. So the research, if you go all the way up to like last year, 2024, they're still sort of trying to work out how to make opals and how opals work. So maybe there'll be another video out when these researchers have answered all the other questions that I've got. Okay, so what do I know so far? Not everything I wanted to know. This rock here is definitely my most expensive piece. The really good opals are worth more than diamonds. This little piece here, I don't know how many carats it is. Might only be 1 carat. Maybe it's quite tiny. It's $37,000. And the special thing about these, they are a lot more colourful than diamonds, and they're extremely rare. So 90% of all diamonds come from sort of this area in Australia. And what happens is you'll find them in these little slithers inside rocks. And so there's silicon that has formed these structures, which I'll show you in a second, little spheres. Now, the other ones that are probably a little bit more, are more common in that last 10% of opals that are found around the world are from igneous rocks, and there's lots of water, so they actually fade and lose color and split. So they're not durable. So the Australian opals are much more expensive because they look better and last a long time and don't degrade. Okay, so that's how they form. Now you can see the little slits. That's what they are. They form in cracks, the silica-rich fluid. And what's fascinating about opals is they're spheres. So if they're not good quality opal, you can't even tell. All right, it's just like a blue silica-looking rock. So you have to do SEMs and actually even eat away the edges, the hydrogel between the silica spheres, so you can see the spheres. So we'll have some pictures of that. And ironstone's a big one. They're bolder opal, and then there's black. So there's a blacker, darker, and then there's some white opals from Adelaide. They're the three main types of opals, and some fossils also form opals. And so this is why they're so hard. This is a black opal. If the opal has settled next to a crack that is black, it shows up really well. And you've got to sort of have the skill to cut it and have a thick enough layer, and then also cut it with the black backing. So that's why it's so expensive. So this one comes from a guy that paid like $10,000 for his rock. I didn't pay that much, but it is the most expensive rock I have, and it's got a nice little red color. So the red one's the most expensive too, which I'll go into in a second. So minerals are two types, silicas and non-silicas. This is my silica page. And opals are considered not crystalline, so they're not really part. That wipes them out from being technically a mineral, so they're called mineraloids. So the silicon dioxide with, I think it's 5 to 20% water. So that's the classification of it. And this is what it is. So silicon form infinite number of three-dimensional shapes, and here they are forming spheres. And so what happens is there's hydrogens or waters that stick to the outside to form that sphere layer. And they get bigger and smaller by forming these concentric layers. So you have this central dense core, and then you get concentric layers over the top. And if it's amorphous, so the circles are different sizes and they're not in a strict order, you'll get that blue opal thing that I showed you before. All right, and you have to cut it open and eat out the matrix with acid, so you can see that there's actually spheres. These ones are elongated. But if they are all the same size and perfectly ordered, that's when you get opal that has color. Now, the reason for that is the reason why I did some earlier videos is structural color. And so because it's a repeating pattern between 10 and 1,000 nanometers, that's the requirement to get light diffracting out. So it's structural. Okay, so the small ones here are the blue greens, and you can see I've got a bit of red as well. But the red can also show all the other colors, and the bit of red I've got, I'll show you here, has all the colors. That little tiny speck goes all these brilliant colors. So diamond certainly can't do that, and I don't think any stone can. So it is not just rare and expensive, but very, very special, and people are constantly doing their PhDs to try and work this out. And I think they've hit a dead end as far as how much I want to know. So the other big thing I want to know is how is the light reflecting? Is it going inside? Because it seems to be too small for light. There's too large a wavelength for that. Although 10 to 1,000 nanometers was my in my structural video was the thing that was, it can be significant for diffraction, but I'm not sure whether it can do the rainbow thing. So I did a rainbow video recently too, and according to this this one here, this physics article, it's both a diffraction, which is around the spheres, which is fine through the hydrogel, but it's also going through the spheres. Now, I don't know enough about periodic dielectric modulation, so I asked AI to check that, and AI says it is, that paper says, means that it is partially through the spheres and around the spheres as diffraction. So maybe sort of a rainbow effect with the spheres and then diffraction around the spheres. And that's where I'm at. So that's all I got for you. Okay.